the previous lecture I introduced the concept of reciprocal lattice vectors and also the concept of plane waves which have the periodicity of the lattice. Now this is actually, if you look at it, it is very simple to understand this, because suppose we have a function which is a function of a single variable which is periodic, f of x plus t is equal to f of x, okay, and I want to expand it in periodic functions. The best periodic functions we know are the sin theta and cosine theta. These are the periodic functions. In fact, sin n theta and cosine n theta. Okay, so let me actually put n also in the brackets. Okay. So now you see that these are periodic in the sense that if I take sin theta plus 2 pi, that is equal to sin theta. Similarly, cos theta plus 2 pi is equal to cos theta. Now if I want to expand f of x plus t and f of x in terms of sine functions, then I should scale my variables, so that if I scale the variables in the following way, that is, if I scale the variables as sin 2 pi x by t times n and cosine n times 2 pi x by t. So if I have scaled my variables, then what you will find is the following, that is sin n times 2 pi x plus t by t is equal to sin n 2 pi x by t plus 2n pi, or that is equal to sin n pi x by t. So by scaling the variables, you have been able to do a Fourier series in one dimension for any arbitrary periodicity. So if you have any arbitrary periodicity, you can always write it as f of x is equal to, I can actually use the Euler relationship that e to the power I theta is equal to cos theta plus I sin theta, and I can write it as sigma over n equal to minus infinity to infinity e to the power I n pi x by t times some coefficient which is f of n. Okay. So let me call this capital F of n. So this is the basic this thing concept behind a Fourier series. Okay. So here what we are trying to do is basically construct functions which have periodicity of the lattice, and also construct functions which only is changed by a phase factor when I translate my function by a lattice constant. So I mean, that is just an aside, I just wanted to tell you as a continuation of the previous lecture. So what we actually did was, instead of the one dimensional problem, if you have an xyz problem, and if the periodicity of the function corresponds to periodic vectors or NLM, which are given by n times a plus m times b plus l times b plus n times c. Then you would use the translation vectors which are in the reciprocal space, which is a, b and c, and you have found that e to the power I k p q r times r has the same periodicity as the periodicity of the lattice, which is that f of r plus r in Lm is equal to f of r. Well, now again we have to construct a Brillouin zone. Okay. We now need to construct a region in K space which is in which no two k points are connected by any reciprocal lattice translation vector. Okay. So, in other words, what I am saying is that I want to construct a region where if I take, I have written as a sphere, but it is not going to be a sphere, it is a polyhedron, but nonetheless just to illustrate the point, I just want to construct a region so that the vector k and vector k prime are not related by a reciprocal lattice translation vector k n. From now on I will call it kp, instead of call it kpqr, I will call it kp, and kp would mean p1 times a plus p2 times b plus p3 times c. Okay, so that is the definition that I have. So, if you want to do this, what you do is you first draw the reciprocal lattice. So, I draw the reciprocal lattice. I am going to draw it only in 2 dimensions because I cannot do it in 3 dimensions, and in 2 dimensions I will do it for a square lattice. Okay. So, in the square lattice, capital A is equal to 2 pi by A and times the x axis, and capital B is equal to 2 pi by B times the y axis. I and j are the unit vectors along x and y. So, now I draw a lattice, preferably I draw a 5 by 5 lattice is better. I can associate with a central lattice point in this case. So, what I will do is I will take the central lattice point. So, let me mark it by a green color, and then I draw all the vectors from here to all the other reciprocal lattice points. Okay. So, I draw, for example, this is one vector, let me forget the arrow, this is another vector, this is a third vector, a fourth vector, fifth, sixth, seventh, eighth. That is enough for now. Now, what I will do is I will draw perpendicular bisectors of the vectors which are joining the central atom with the central reciprocal lattice point with the nearest neighbor or the next nearest neighbor reciprocal lattice points. So, these things I will show in a different color. So, these are the perpendicular bisectors. Okay. Now, I will look at the innermost region which is closed. So, the innermost region that is closed is having this shape. So, this is the first Brillouin zone. So, let me mark it by a shaded curve. Okay. And then the second region which is between the innermost region and the next closed region is the second Brillouin zone. Okay. So, let me mark it by a different color. So, that looks like this quantity, right, that is. So, this is the regions. Okay. Now, it is possible to, because if you translate by a reciprocal lattice translation vector, things are not going to change in your system. Okay, because that is what we have seen because of Bloch's theorem, we have seen that already. So, which means the following, that is, I take this portion and translate it down by a reciprocal lattice translation vector. When I do that translation, then what I get is this region. Okay. And similarly, I take this region and translate it in this direction, and what I get is the following. This region, and I can do with the other two, in which case I will get the entire square inside. So, the reason is that what I am trying to show you is that the second Brillouin zone has the same area or volume as the first Brillouin zone. Okay. So, in this fashion you can keep constructing Brillouin zones which are further apart. For example, I can draw one more perpendicular bisector here, another one here, another one here, and another one here, and now I can put all the regions between second and third Brillouin zones and get back to first Brillouin, get back a third Brillouin zone, and that I can actually show it in a different form. Okay. So, what it actually means is that all the Brillouin zones have the same volume, and the point that you take as the central point around which you do all these things are really any arbitrary lattice point. If you do the same construction done in real lattice, in real space on real lattice, we get what is called a Wigner-Seitz cell. Wigner-Seitz cell, and this Wigner-Seitz cell is useful in many contexts, particularly in calculating the cohesive energies of metals, and I do not know whether I will have the opportunity to talk about it, but nonetheless I just want to give you the parallel that if you construct in the real space, what you get is a Wigner-Seitz cell. If you construct it in the reciprocal space, what you get is a Brillouin zone. So, that is the difference between the two things. Now, for a Brillouin zone, we said that no two k points, k vectors in a Brillouin zone can be connected by a reciprocal lattice translation vector. So, what it means is that the boundary of the reciprocal lattice, the boundary plane of the Brillouin zone is then given by k prime is equal to k plus kn, where k and k prime are on the boundary of the reciprocal lattice, or on the boundary. So, for example, I can draw it this way, that is, I have a Brillouin zone here. If k and k prime should be related by a reciprocal lattice vectors, they must have the same length, and this is the reciprocal lattice vector k1. Okay. So, if k and k1 are on opposite sides and they must be reflected, so because of that the length of the vectors k and k prime must be the same, which means that k prime squared, which is the length squared, is equal to k plus kn squared, or I have k prime squared is equal to k squared plus kn squared plus twice k dot kn. Now, k prime squared is equal to k squared because they are reflected points on the surface, both of them are on the surface. So, because of that I have the condition kn squared plus 2k dot kn is equal to 0. So, this is the condition for boundary plane of a Brillouin zone. So, this is how you define the boundary plane of a Brillouin zone. Well, I have shown you how to construct Brillouin zones, and based on this I now know that when I do an energy band calculation, we restrict all the k points to a Brillouin zone. So, you can do all the k points. So, you can do the same things as before, that is you can do the S band, the P band, the D band, etc., and all the bands correspond to wave vectors k which are within the first Brillouin zone, and you can get the energy band diagrams which are very detailed, or you can get just the density of states, or like chemists you can just get the top of the band, bottom of the band, and then just say that is a band. So, these are different ways of looking at it. Now, having introduced this concept, the next thing that I want to do is to approach energy band theory from the point of view of a physicist. So, in physics, the energy band theory approach started from free electron. You could ask the question, why did people start with free electrons? The reason why one started with free electrons was simply because the electrons in metals, for example, were conducting. In other words, they were moving freely through the lattice, it appeared, and so they said that free electrons must really be present in metals, and so we can, as a first approximation, we can deal with electrons in metals as free. Now, the question is it really true that they are free? Okay. So, let us see whether they are really free or not. Okay. Let us look at sodium metal. Sodium has atomic number 11, right. That means you have 11 electrons per sodium atom. Per sodium atom, and the sodium distance is roughly about 3.7 angstroms. So, let us take it as 4 angstroms. Okay. 4 angstroms are 4 into 10 to the minus 8 centimeters. Okay. Now, there is one sodium atom, this is an approximation, one sodium atom in a sphere of volume, say 4/3 pi 2 cubed, these many angstroms cubed. Okay. So, that is because what one is, we are taking the distance between sodium and sodium as 4 angstroms. So, you take a sphere of radius 2 angstroms, and within that there is one sodium atom, and similarly you have another one, but we are ignoring the voids between the spheres. So, but that is just an approximation, it is a hand waving argument that I wanted to give you. Now, what is the volume of this? The volume of this is actually 2 cubed is 8. So, roughly is about 10 pi angstrom cubed, or I can even say that it is about say 32 angstrom cubed. Okay. So, in about 32 angstrom cubed, am I right? So, yeah, because pi and 3 may roughly cancel. Okay. So, that is very, very crude. Okay, in 32 angstrom cubed we have 11 electrons in 32 angstrom cubed, or you have roughly 1 electron per 3 angstroms cubed. Okay. So, if it is 3 angstroms cubed, then what is the radius? The radius in which you find only 1 electron, the sphere radius in which only 1 electron is found is of the order of cube root of 3. So, cube root of 3 is roughly maybe about 1.3, roughly about 1.3 angstroms I think, because 1.3 will give me about close to 1.8, 1.8 into 1.3 will again give me close to 3 angstroms cubed. Okay. So, I mean these are all just order of magnitude calculations. So, you can correct these numbers, and but I am just trying to give you for illustration purposes. So, it means average distance between electrons is roughly 2 angstroms. Okay. So, the potential energy of interaction between 2 electrons is E squared upon 2 angstroms, or roughly E squared upon 4 Ah, where Ah is the Bohr radius. Bohr radius is 0.529 angstroms. So, I have just taken it as 0.5 angstroms. Now, energy of an electron in first Bohr orbit which is the same as, or which is the same as the energy of the 1s electron is E squared by 2 Ah, about 13.6 electron volts. Okay. So, what we are looking at is electron repulsions are of the order of say 7 electron volts. So, you really cannot say that electrons are free in metals, but because there is a very, very high density of electrons in metals, and because of this very high density the mean distance between 2 electrons is rather small, and when the mean distance between 2 electrons is rather small, the repulsive energy is large. So, they are really interacting and they are not free, and they are also bound to the nucleus. Okay. So, electrons are not really free in that sense. So, but still the free electron theory was based on, because it was much before Bohr's theory and so forth, the classical free electron theory, and so it was based on the observation that the electrons were moving freely in a lattice as illustrated by either the thermal conductivity of a metal or by the electrical conductivity of a metal and so forth. So, people did assume that the electrons are free, but there is also another reason which we will come to later on based on what are called the pseudo potential theories, which actually tell you why you can actually get away by assuming that the electron repulsions are weak. Okay, but that has a deeper reason, and we will, that requires understanding of the phase shifts in electron scattering, that we will talk about at a later time. But for now what I am going to do is that just illustrate the fact that the electrons are not free, but still we use the electrons to be free. So, if the electrons are free, free electrons have only kinetic energy, okay, and the energy is given by the kinetic energy, which is given by p square upon 2m. P is the momentum, and m is the mass. And because my Hamiltonian for the free electron is just p square upon 2m, okay, what we have is that the eigenstates are e to the power I k dot r, where and momentum is h cross k. Okay. So, one can start with this free electron theory and you can derive a lot of properties of the metals, and classical free electron theory sometimes gives you correct results, but that is purely accidental, and I will come to that one in the next lecture why it is purely accidental. But in quantum mechanical theories you will get a little bit better understanding based on Pauli exclusion principle, how you can actually show what the specific heats of metals are, and how you can actually explain the fortuitous correctness of the classical theories. That I will discuss again only in the next lecture and not in this lecture. And in the next lecture what I will also do is, apart from dealing with the classical theories and the quantum theories, without introducing the underlying lattice, I will go on from there to discuss when we have an underlying lattice what happens, how we can treat the potential as a weak perturbation over the free electron gas and try to get all the energy band pictures that we actually obtained from the atomic orbitals with which we started. So, these things I will discuss only in the next lecture, and I think this is a convenient point for me to stop this lecture, and we will continue it again in the next class. Thank you.